We have a couple of examples involving friction here, so let's take you through those things. And one thing to remember when we're solving problems using friction is really just another force. And we're going to utilize it exactly the same way that we've been using different forces with our system. So, the first one, an object with a mass of 15 kilograms is placed on a surface. Starting from rest, the object is accelerated at a rate of 2 meters per second by a force of 80 newtons. What is the force of friction acting on this block? So, we're going to start this exactly like we have been. Right, here's our object. It's on a surface, so there's a normal force pushing up. The weight of the object is going down. There's some applied force, I'm going to label it F sub A, that's equal to 80 newtons. And then the force of friction's job is to oppose motion. So the force of friction is acting in this direction. And we know there's an acceleration because the problem tells us that there's an acceleration. So therefore, we're going to start by saying the sum of the forces is equal to m times a. And we know that this applied force in this particular case causes the object to accelerate to the right. So we're going to make the right positive and the left negative. So therefore, FA minus FF is equal to m times a. What is the force of friction acting on this block? Again, we've done forces like that. We've done problems like this where this maybe is a tension force 1 and that's a tension force 2. Well, the only difference in terms of how we're solving this is what we're calling this particular force. We want to find FF. Okay, well, algebraically, it's just the applied force minus MA, and that is equal to the friction force. So there's lots of conceptual stuff that we have to learn about the friction force. However, when push comes to shove and we're problem solving with respect to it, it's exactly the same as any of the other forces. So now we think about our thought process. Do we know FA? Yeah, it's 80 newtons. Do we know M? Yeah, it's 15. Do we know A? Yeah, it's 2. So therefore, we know all these numbers. We can figure out that friction force. 80 newtons minus 15 kilograms times 2 meters per second squared is equal to the friction force. Well, 80 minus 30 gives me 50, so we have a friction force of 50 newtons. Now, let's think about that. Does that make sense? Right? Well, a month ago when we started talking about all this stuff, if I would have told you there's an 80 Newton force going this way, like this, and there's a 50 Newton force going this way, as per that, you would know that the net force is equal to 30 newtons to the right, and the sum of the forces divided by m equals a. So our sum of our forces are our net force is 30 newtons divided by a mass of 15 kilograms would give us an acceleration of 2 meters per second squared. You would have known that. So friction force isn't much different. So we got a situation over here where my picture looks similar. I've got an applied force going this way. I've got a normal force pushing up from the surface. The weight of the object is acting downwards. And there's some friction force pushing back this way. Now the object is accelerated, so we know that the sum of the forces equals m times a. Now, if this object were moving at a constant speed, we would still draw a picture. The picture could be the same picture. The sum of the forces wouldn't equal ma anymore. It would equal 0. We've got our same sentence, right? Applied force minus friction force is equal to m times a. What is the value of the applied force is our first question. So I got to solve for FA. FA equals FF plus m times a. So I start this process. Do I know the acceleration? Yeah, it's 2 meters per second. Do I know the mass? Yeah, 22.7 kilograms. Do I know the value of the friction force? Well, no place up here does it tell me the value of the friction force. Now, it does tell us the value of the coefficient of sliding friction, and we know that that is just an indicator of the surfaces in contact with each other. but that's not the value of the friction force. So I've got to go someplace else to find the value of the friction force. Well, what can I always substitute in for the value of the friction force? Mu times the normal force, because that's our main equation for what the friction force actually is. So now let's start the process over again. Do we know A? Yes, it's 2. Do we know the mass? Yes, it's 22.7. Do I know the coefficient of friction? Yes, 0.65. Does the problem tell us the value of the normal force? No. But because the object is not accelerating vertically, we know that the normal force is equal to the weight. So we can take everything and substitute the normal force with the weight, or weight for the normal force, rather. Now we start our process over. A is 2, M is 22.7, mu is 0.65. Do we know the weight of the object? Again, no place up here do we know the weight of the object, but a substitution we've been making for a while now is to substitute M times G for W. 0.65, 22.7, 9.8, 22.7, 2. Now we can substitute all of that stuff in there. 0.65 times a mass of 22.7 kilograms times 9.8 meters per second squared plus 22.7 kilograms times an acceleration of 2 meters per second squared. FA is equal to 144.6 newtons plus 45.4 newtons. My applied force has a value of 190 newtons. Now, the next question, what's the force of friction? Well, we've actually figured that out in our process. FF is mu times the normal, is mu times the weight, is mu times M times G. Substitute all that in there. The actual force of friction is 144.6 newtons.